This is page 1 of the review for your test on two-dimensional geometry and measurement. Problem 1 has a lot to do with naming angles, measuring angles, understanding angle relationships. It says in the figure below, points B, C, and D lie on line M. So points B, C, and D, these are all on this line, labeled line M. And we're asked, what is the measurement of angle CBA? So we need to trace angle CBA. Go from C to B to A to understand that they're talking about this angle right there. And so I can find angle CBA if I understand that this angle, this 135 degree angle, and angle CBA are supplementary. And so supplementary angles have a sum of 180 degrees. I mean, you can see that if I add this angle to this adjacent angle CBA, they form this half circle. Half of 360 degrees is 180 degrees, and they form this line, which is a straight line, straight angle. Anytime you see the word straight, if you have a pair of angles that make a straight line, they are supplementary. Both straight and supplementary start with the letter S, so that might help you remember. So I take the 180 and I subtract the 135 to find out the measurement of CBA. And that difference is 45 degrees. And when I place that measurement on this angle, that looks like a reasonable measurement because it looks like about half of a 90-degree angle. So angle CBA is 45 degrees. Next question asks, what is the measure of angle BCA? Now that's B to C to A. C is the vertex, so now they're talking about this angle. And again, we have a pair of supplementary angles. 150 plus what equals 180? That one you can just do mental math. It's 30 degrees. So 30 degrees. The next question, what is the measurement of angle BAC? BAC, with A, the middle letter being the vertex, BAC is this angle up here. Well, if you consider triangle BAC, we have two of the angles of the triangle, and we're trying to find the third angle. Well, the angles of a triangle add up to 180 degrees. So 45 plus 30 plus angle BAC have to add up to have a sum of 180 degrees. And 45 and 30 is 75. So 75 plus what equals 180. You could do 180 minus 75, or you might just be able to see that this has to be 105. I'd have to add 105 to 75 to get 180. So this angle is 105 degrees, which makes it obtuse and a little more than 90, and that's what it looks like to me when I look at it. So this looks reasonable, 105 degrees. Next question asks for the measurement of angle DAC. DAC is this angle. DAC. Well, now we need to focus on, let me just sort of highlight the triangle we're looking at now. This triangle. And we still have 2 out of 3 angles because we see this square symbol. We know that means 90 degrees. So I have a 90 degree angle and a 30 degree angle. I need to know this missing angle. I'll just call it X. 90 plus 30 plus X equals, again, 180 degrees for any triangle. So this is 120 plus X equals 180. So X must be 60. 120 plus 60 will give you 180. So this angle is 60 degrees. That looks about right. This next question asks, how would you classify this pair of angles, DAC and DCA? Well, DAC is 60, and DCA, D to C to A, that's the 30 degree angle over here. And 60 plus 30 equals 90. So a pair of angles that add up to 90 are called complementary. Complementary. How would you classify this pair of angles? BDA. BDA is this right angle, this 90-degree angle, BDA. And CDA. CDA is this other right angle. So 90 and 90 equal 180. Those are supplementary angles. Okay, problem 2 on your review. Convert the rational numbers below from fraction form to standard decimal form. Use bar notation to represent repeating decimals. So we learned that pi is the most famous irrational number, a number with decimal that never ends and has no repeating pattern. Any other decimal number that either terminates or has a repeating pattern can be written as a fraction. So 2/3 is already written as a fraction, so we know it's a rational number. We can convert it to a decimal. Sometimes you have many options. If we could multiply 3 by some number that would give us 10 or 100 or 1,000, we could create a decimal fraction, but 3 is not a factor of 10, 100, or 1,000. So we have to use the other method, which is divide. We know that the fraction part of the vincula means divide. So 2/3 can be thought of as 2 divided by 3. And so if you do long division, 2 divided by 3, and ask how many 3's are in 2, there are 0 3's in 2. But I want to keep dividing, so I just express the 2 as 2 and 0/10. It was always 2 and 0/10, we just weren't showing the 0/10. So we just revealed the decimal and the 0/10, line up a decimal in the quotient, and ask how many 3's are in 20. There are 6 3's in 20 because 6 multiplied by 3 is 18. We subtract, we get a difference of 2. Reveal the 0 in the hundredths place and bring it down. Again, how many 3's are in 20? 6. 6 multiplied by 3 is 18. Subtract, you get a difference of 2. We're going to keep doing the same pattern. I'm going to keep getting 6's here. So 2/3 written as a decimal is 0.6666. The 6 goes on forever. But we can represent that with bar notation as 0.6 repeating. You just put a bar over the 6, and that tells somebody looking at your number that the 6 goes on forever. That pattern repeats. 7/9, we'll do 7 divided by 9. How many 9's are in 7? 0. I'll reveal the 0 in the tenths place and line up my decimal and my quotient. How many 9's are in 70? 7 9's is 63. Subtract, I get a difference of 7. Reveal the 0 in the hundredths place and bring it down. How many 9's are in 70? Again, 7. 7 multiplied by 9 is 63. And we're going to keep getting this pattern. And so this one is 0.7 repeating. 0.777 infinitely. I'll definitely be asking you to convert a fraction into a decimal using long division on the test. Problem 3 asks us to find the exact area of this figure below. This is a composite figure. It has a curve, so it's not even a polygon. We have to figure out how can we break it up into shapes. And this one's pretty straightforward. If you draw a line here, then you have a rectangle. Shape 1 is a rectangle. Shape 2 is a little bit trickier. You know it must have something to do with a circle because of that curve. If I draw a full circle and think about what half a circle would look like, does this piece look like half a circle? No, it doesn't. But if you think about a quarter of a circle, this piece right here, that's what we have. We have 1/4 of a circle because we have a 90-degree angle here, so that's 1/4 of the 360 degrees. So we're going to use the formula for a circle for area 2. Area 2 is equal to pi r squared, but we'll just take 1/4 of that. We'll just say it's 1/4 of pi r squared because it's not a full circle, it's 1/4 of a circle. And it says exact area, so I'm not going to substitute a value for pi. If I substituted any number for pi, it would no longer be exact, so we're just going to leave pi as pi. So area 2 is exactly equal to 1/4 multiplied by pi multiplied by the radius, which we haven't figured out yet, so let's look at that. For the radius, you have to recognize that if this distance is 12 and this distance is 9, then this distance must be 12 minus 9 or 3, because the 9 and the 3 have to add up to this 12. So if this is 3, this is 3, the radius of our The distance from the center to the edge of that quarter circle is 3. The radius is 3. So we'll substitute 3 for the radius here. We're squaring it. So I have area of shape 2 is 1/4 multiplied by pi multiplied by 9. And we can just multiply the 9 by the 1/4, so we get 9/4 pi. Area 1 is straightforward because it's just a rectangle. It's base multiplied by height. And the base is 12 and the height is 7, so 12 times 7. Area 1 is 84. The area, the total area, is equal to area 1 plus area 2. So the area is equal to 84 plus 9/4 pi. And then you would need units, centimeters squared. Or if you expressed the 9/4 as a mixed number, you could say 84 plus 2 1/4 pi centimeters squared. Or if you express if you express this as a decimal, you would have area equals 84 plus 2 25/100, 2.25 pi centimeters squared. And any one of those is a good answer. They're all equivalent. Okay, that completes page 1. We'll pick up the review with page 2 on the next video.